Hello, this is part two of the shapes example, part two of the inheritance and shape factory example. Now, in the previous two examples, examples one and example two, in part one of this discussion, we looked at an example shapes inheritance hierarchy where we got a shape interface that consisted of a perimeter function, an area function, and a clone function, all three of which were pure virtual functions. And then we had a virtual display function, a virtual function, where the shape base class provided an initial implementation, some sort of basic implementation. In this case, outputting the name of the shape. Then we look at a few examples of shapes that could extend that: square, circle, triangle, right triangle, equilateral triangle. And then we, in the second example, looked at an extension of that with the factory model, abstracting away the logic of which shapes I can create and keeping track of which shapes I can create. And then at the end of that example, at the end of that discussion, I made a note about this array of shapes and how it is very likely that in a less academic exercise, meaning something that's not written purely for the sake of discussion, that I'll be working with collections of these shapes quite often. And instead of manually writing the code for the array each time, or the code for a vector of pointers, or a list of pointers, or a linked list of pointers, or whatever the data structure might be, instead of writing such a data structure from scratch each time, what I would like to do is I would like to abstract away that logic, provide an interface through which I can store and retrieve shapes. Now, what I have on the screen right now is where we left off with example 2, a pointer to an array of shape pointers. And we see that I allocate the array of shape pointers. I create each shape through the shape factory, where create shape is a static function. I then output each shape. Then when I'm done, I delete each shape and delete the array itself. In example 3, we see that I've replaced all that logic with these few lines. So in example 2, I had all the logic to create the array, output everything, clean up and delete it. And in example 3, by introducing the shape collection ADT, I've reorganized that logic. I've abstracted away the details. Now we know that here I'm creating a shape collection object called shapes, and I'm passing in some initial value 5. Now, the importance of that value of 5 we'll discuss in a few minutes, but I'm creating a new shape object, and there is a constructor that takes a single integer. I know that based on how that line's written. I am then creating each individual shape as I did before, but instead of assigning it to a position within an array, I am calling the add shape member function of my shape object. In this case, shapes is a shape collection object, and I'm calling the add shape method. So from inside out, I am creating a shape with the name triangle, and I'm allowing the shape factory to do that. I'm taking the pointer it returns and adding it to my shapes object, my shape collection object. Now, internally, how my shape collection object stores this, I don't know. All I know is it stores it. And add shapes adds it. Right? One of those self-documenting variable, excuse me, not variable, but function names. Now, I've called it add shape here to emphasize what it's doing, but if I were to change its name, I would call it something more along the lines of add or append, or probably push back to follow the C++ vector interface. But for now, we will stick with add shape. And this adds the shape to the container, to the end of the container. And then I output the shape object. Now, there's a key piece of insight I need to remember. Anytime I see something like this, where I'm outputting an object like this, operator overloading. The stream insertion, the output operator, has been provided for the shape collection object. Which means if I compile this code, let me run the correct make file. If I compile this code, I should get no compilation errors. And let's just do that from scratch. We can see that everything compiles without issue. Now, if we think about it, we already know how to write a shape collection container. We already know how to provide this interface, an iterator, a constant iterator, begin and end functions, that sort of thing. Now, for the sake of brevity due to time constraints, I'm going to forego the formal iterator, begin, end functions, the formal container interface, and discuss a partial implementation of a shape collection, where we could easily extend it to include begin and end functions. So now I'm in the shape collection header file for this shape collection object I've created. You can see I've provided two iterators, an iterator and a constant iterator. Now, based on the type defs I provided here, we can tell that my iterator is really a vector iterator for a vector of shape pointers. And we can see that within the shape collection ADT, within the shape collection class, I have a private data member, which is a vector of shape pointers called shapes. Remember, scope. The shapes here is a vector of shapes. The shapes in here is a shape collection. Two different scopes, two different functions. Not a problem. But keep that in mind. So within the shape collection class, I have this shapes vector of shape pointers. Now in assignment 3, you're working with a pointer to an array of pointers, and we could easily have implemented shape collection using an array of pointers if we chose. But the point we need to remember is it does not matter what this internal data structure is, as long as the interface shape collection provides is consistent. Meaning, as long as the interface does what it says it will do, the implementation details are another story. However, it can be implemented however I want to implement it, I can implement it that way, as long as I provide the iterator, the begin and end function in the same interface. As long as I do that, I can use whatever data structure I choose. Here I chose a vector of shape pointers. I then have my default constructor. I then have a constructor that takes a single integer n and allows me to reserve space, and I'll get to that more in a moment. I then have my copy constructor, my destructor, a size function to get the number of shapes in the container, the size of the container, an add shape function to add a shape, a stream insertion operator, and once again, here we'll use the copy and swap idiom as opposed to the larger copy and paste method we discussed in assignment 1. Our standard display function, and a swap helper function which I've implemented as a friend function here. Now all this does is allow me to swap two shape collection objects. Swap the values they contain, just like the standard swap would do for two integers or two any other data types. Now I have provided a link to a Stack Overflow article, and it's very uncommon that I find a Stack Overflow article or post that I would link to for sake of discussion, but do take a look. That does provide, it does list some very interesting points in some of the responses there. So the swap function, which we're going to use to implement our assignment operator. The inline size function. The stream insertion operator, which is once again a little more than a wrapper for our display function. And then shape collection.cpp. My default constructor with an entry in my initializer list for the shapes vector. Now, once again, is this necessary? No. The compiler will add this call implicitly, meaning automatically even if I don't. The second constructor that takes an integer, I'm calling the vector reserve function. Now, the reserve method in the STL for STL containers such as vector allows you to indicate how much space you plan to be using. For example, if I said reserve 5, this would reserve enough memory for 5 elements in my vector. If I want to say 1,000, it would reserve enough for 1,000 instead of allocating on the fly. A little optimization detail, something added in C++11, a very useful optimization if you have a use case for it. But it's a good thing to know. I get down to my copy constructor, and you can see range-based for loop. One of the reasons I chose the vector, so I can use a range-based for loop. Now what I want to do is, for every shape in my source shapes vector, remember, in a copy constructor, you want to copy the source data and perform a deep copy, provide a deep copy, provide a separate yet identical set of data. I am grabbing a copy of every pointer in the source shapes vector. I am then taking that pointer and cloning that source shape, copying it. So cloning it. In assignment 3, that'll probably end up being something more along the lines of this polyhedra I equals source.polyhedra I arrow clone. But it's similar with a more traditional count-based for loop. I equals 0, I less than the size of my array, I plus plus. But the premise is the same. The process is the same. I want to clone those shapes. I don't want to copy the pointers. I want to copy the data referenced by each of these pointers. In assignment 3, you're simply doing an array of pointers instead of a vector of pointers. Implementation detail. The fundamental process is the same. Same for my destructor. Range-based for loop. Traverse my vector of shapes and delete the block of memory referenced by each shaped pointer. Now, if you think about it, for a vector, I would write something like this. But if I were working with an array, if I were working with a pointer to an array of pointers, I would have something more like this. Right, in assignment 3, this might be num polyhedra, polyhedra I, delete polyhedra. But this is very similar to what you would find in a destructor in assignment 3 for a pointer to an array of pointers. It's more or less one of those standard template lines of code, if you want to call it, standard code snippet, right? Deleting an array of pointers. Delete everything in the array, delete the array itself. Now jumping back to example 3, we finish the destructor, and then we get to add shape. I'm going to jump back to the header file and explicitly note this precondition. I've documented the precondition as toAdd is not equal to null. Now, in this case, I'm explicitly checking that condition, and I'm saying if toAdd is equal to null, return false, indicating I could not add it. Otherwise, add that pointer to my vector, push shapes.pushback, and return true, indicating success. Once again, similar to our previous discussions. Similar to assignment 1, similar to the house example, the room renovation example from earlier in the semester. I'm adding it to the end of my data structure, in this case a vector. I then get to my assignment operator, and this is where we apply the copy and swap idiom. Now, one thing you will notice is this is pass by value. Another term for pass by value is pass by copy. I am passing in a copy of the right-hand side. I am then taking the contents of that copy and swapping them with this shape collection. I'm swapping the contents of this shape collection with the copy of the right-hand side shape collection. I am then returning a reference to this shape collection. So what's happening here? Here, because it's passed by copy or passed by value, the copy constructor is being called implicitly, which is why we need the copy constructor. As soon as I return a reference to this and this function exits, this right-hand side shape collection is destroyed. I passed in a copy, swapped the contents of this with that copy, and then the right-hand side with those changed contents is deallocated. So while I would normally, in an earlier version of this, copy and paste my destructor code, then copy and paste my copy constructor code, I have, through the copy and swap idiom, that's idiom IDIOM, through the copy and swap idiom, perform the copy implicitly with a pass by copy. Swap the contents of that copy with this. Return this with the copied contents, with those swapped contents, and allow the original data to be destroyed through an implicit call to the destructor on the changed right-hand side. Then we get down to the display function. For every shape in the shapes vector, grab that shape pointer, dereference it, and pass a reference to that shape into the shape stream insertion operator. This is identical to what we were doing in example 2. The only difference being, in example 2, shapes I is a pointer in a shape array. In example 3, S is a shape pointer on its own. Same process. Then the swap method. The only data for a shape collection I have to swap is the STL vector. And because the vector is a built-in container, part of the C++ STL, there's a predefined swap method for vectors. And all I do is swap the left-hand side with the right-hand side. But all I've done is I've taken example 2, said I'd rather use a vector, and I want to just put a wrapper on that. I want to write this code once, generalize it, provide this specialized shape collection container, and just be able to use that to work with a collection of shapes. And now if I run this, we see we get results similar to example 2. All we've done is taken all the shape collection logic, grouped it together into a formal shape collection class, made use of the shape collection object, and reorganized our logic. But the underlying process, the underlying mechanics are still the same. We still have the same calls to the shape factory, and we still output all the shapes with pointers calling the appropriate display function. The same dynamic binding, the same virtual functions, everything. Same thing takes place. So now we're making use of the clone function and the shape collection to perform a deep copy, and the shape factory when we need to create a copy. So clone is providing, this clone function is allowing us to exploit dynamic binding and use a wrapper to call the appropriate copy constructor. But one thing you might notice is I'm explicitly creating these shapes and I'm hard coding them into the program, which is very nice for a quick discussion or a more formal discussion or like that to emphasize what we have, but it's a very, very restrictive way to create shapes. So what we'd like to do is we'd like to go ahead and say, let's close example 2 and keep example 3 up. This is the example 3 run shapes. What we would like to do is we'd like to take this and extend it so that we can read shapes from an input file. Read the shapes you want to create from an input file. And for that, we're going to move into example 4. So right here, we have the example 4 run shapes. Okay. And as we move through, we will see I've introduced a new function in example 4 called read shapes. This will take an input stream. And by input stream, that could be CN, an input string stream, an input file stream, anything that extends the iStream interface, be it CN or an input file stream, as we will use here. Now this does accept command line arguments, so we have our standard command line argument checks. Do I have the correct number? If not, output a usage message indicating to the user how this program should be invoked. Open the shapes file specified at the command line. If I could not open that file, explicitly indicate such with an error message. And then the rest is the same as before. Set the decimal places, the number of decimal places for my precision. 4 decimal places, fixed decimal notation. And just like before, output the heading available shapes. Call the shape factory list known function. Print a horizontal dividing line. Print the number of known shapes, the number of shapes available. And output a blank line. And now we see that line 73 has replaced lines 93 through 98 in example 3. We had lines 93 through 98 where we were explicitly creating each shape by hard coding calls to the create shape method. In example 4, we've changed that so that we create a shapes object and we assign it the value of a shapes object we return from this read shapes method. Now to read these shapes, we pass in the shapes file input file stream, pass it into read shapes, and we get a shape collection as a return value. We then take that shapes collection and we output it just like we did in example 3. The only thing that's changed is instead of hard coding calls to create shape, I have now created a read shapes function that reads a text file, makes the appropriate calls, constructs the shape collection container, returns it, and then I output it. Now, let's open that input file. And you'll see all I did here is take the shapes I was creating originally, triangle, right triangle, equilateral triangle, square, circle, and the shape we know we can't create. And I simply put them as lines in an input file. Now, because of these spaces, we know we're going to need to use the getLine function call. So what's happening here? Well, in the readShapes function, I'm creating a local shape collection called collection in this case, right? But let's use a different name, collection. I'm creating a new string name, which is going to be the contents of each line. This line right here is a very nice trick. WS is a flag, a buffer, essentially. What this line will do is it will read any leading white space. It will strip off any white space from the input stream, be it spaces or tabs. Strip off all leading white space. Then use getLine. How do I use getLine? GetLine, the input stream. I want to read from this input stream and store it in my string variable. Okay. Now that I know the name of the shape I want to create, I'm going to take that name and pass it into the shape factory create shape method. I am then going to take the shape I created, that pointer. I'm going to assign that pointer to S, the shape pointer. So after this line, I have a shape pointer S, which references the shape created by the create shape method of the shape factory. Now this is either a pointer to a shape or null pointer if that shape does not exist, if it cannot create it. For example, if we have the 1337 hacksaw shape, which is the lamest joke ever, but I wrote it, so I guess I'll just keep doubling down on that joke, right? Still a bad joke. Anyway, then what happens is now I say, I only want to add it to this container if S is not equal to null. If S is not equal to null, pass S into add shape, add it to the shape collection container just like we did before, strip off any trailing white space, repeat until I've read the entire file. Then, for verification purposes, so I can see the collection, I output it here. And if I weren't discussing this, I would eventually comment this line out, but for the sake of discussion, I've added an output to this function. So we are going to see this shape collection output twice, once as collection within readShapes, and once in the final output in the main function. But this just repeats, repeats, and repeats. So now all I've done is made the very simple change of saying, you know what? Instead of hard coding the shapes I want to create, I want to be able to read strings from an input file, pass them into the shape factory, and have that created. So all we've really done is added the ability to read a list of shape names from the file. Everything else has remained the same, except for a very subtle change in shape collection.h. Now we still have the same precondition, but now I'm added an assertion. Now I'm saying if at runtime toAdd is equal to null, that should not have happened. Program needs to terminate if it's running in debugging mode, right? If I have assertions enabled, which by default in C++ they are. So if I have a precondition, I can either check it and handle it. I can add an assertion to check it and halt, right? Throw an assertion, raise an assertion error, or I can assume it's true. I can take any of those approaches. Okay, so now we can read the shape names from an input file. We can continue to read that file, and that's it. That's all example 4 really adds. Nothing too interesting there, right? Read from an input file, all of that. Well, I guess that's it then. Nope, there are 2 more examples. We can take this a little bit further. So let's look at what's added in example 5. I'm going to close example 3, and I'm going to keep the example 4 version of RunShapes open in this tab here. And now we get to example 5. You can see I'm only modifying run shapes and shape collection at this point. So I'm simply building on top of what we've already discussed. Okay, so example 5. I still have the read shapes function. Remember, I'm going to add to this. It still looks about the same. Right, the main function is the same as it was in the previous example. Right, example 4, example 5. Now let's scroll down to the read function. And let's do the same in example 5. And now we can see, going from example 4 to example 5, I have changed the read function a little bit. I have now said, you know what? I want to abstract away this detail here. So now instead of having a string variable name, I've moved my shape pointer s to the beginning here. I'm still stripping off the leading white space. But instead of a getLine call here, I now have a stream extraction operator that reads into a shape pointer defined. I'm going to do some hand waving and just say line 95 works, accept it for the moment. I then get to line 96 and it's the same as before. If my shape pointer s is not equal to null, add it to my shape collection, strip any trailing white space. And then, for verification purposes, let's output collection so we can look at it and see what we get. Now, we get back to line 95. How does this work? Well, since the beginning of the semester, and hopefully in CS 250, it was emphasized that you should always provide a display function, specifically an overloaded stream insertion operator for output. And now we're going in the opposite direction. And by that I mean, well, let's call it the complementary direction. We're complementing that. Yes, we still need to display, we still need to be able to output things, but it would be nice if we could also input things. We could extract them from an input stream, read from an input stream, read from CIN or an input file, and if we could abstract away the details of that logic. So now is where it gets interesting. There are really only two places I would define a shape stream extraction operator: within the shape header file, and meaning shape.h, shape.cpp, or within the shape factory, shape.h or shape.cpp. So I know those are one of the two places. Let's just guess shape collection. Well, not shape collection, excuse me, shape factory. Let's guess and say I've implemented the stream extraction operator and defined it within shapefactory.cpp. And we can see that is in fact the case. I have written it here and implemented it here. Now, why did I implement the stream extraction operator to read a shape within the shape factory? Well, the key reason being the implementation details of this are provided by the shape factory, meaning the shape factory creates the basic shape. So all I've really done is I've factored out the inner part of that while loop and I've pulled it out and abstracted out the logic into a separate function. If we look, I have a name variable, a string, the name of the shape I want to create. And now things get interesting. Now if I look at this version, the example 5 version of input shapes.txt, I now have the shape name, a semicolon, the values for that shape. The shape name, a semicolon, the values for that shape. And one thing we will notice is each shape has a different set of values. A triangle has 3 floating point values. A right triangle has 2, the base and height. An equilateral triangle has 1. A square has 1. A circle has one. And this shape is somebody trying to break it. Fine. So what we're going to do is, we know that there exists a form of the getLine function which reads from an input stream into a string and stops at a user specified character, in this case a semicolon. I am then into my shape pointer RD for read or read, let's call it read. Into my shape pointer read, I'm going to store the result of passing the name string into the create shape method of the shape factory. Right. This line is similar to before. I've just changed from a shape pointer S to a shape pointer RD for read. If RD is not equal to null, I'm going to make a call to a shape read function. If read is equal to null, the rest of that line is garbage. I'm going to read the rest of that line. So if the line's garbage, I'm going to read the rest of that line and throw it away. So if I have a pointer to a shape and not a pointer to null, meaning I was able to successfully create a shape, I'm going to call that shape's version of the read function and pass in the input stream. Wait a minute. I don't remember discussing this. This is new in this example. Right? Just like each shape has to be output slightly different, there's different information I want to output for each shape. There is different information I want to read for each shape. So what I've done in example 5 is I've pulled out the reading of a shape into this shape stream extraction operator. And I've introduced a read function so we can exploit dynamic binding so that each shape can provide the code it needs to read its values from an input stream. Be it a single number, 2 numbers, 3 numbers, doesn't matter. So now, if we open up shape.h and we scroll down all the way to the end of the class definition, we see that I've added a pure virtual function read. Now, read is pure virtual because there is no way for me to generalize this. Right? There is no common value I read for each shape. Reading that shape name is handled outside the shape. All the shape does is read in the values it needs to create to initialize its attributes, if you will. So there is no initial implementation. It's a pure virtual function. Okay, now these read functions are going to be very complicated. They're some of the most complicated code we will write this semester. So let's open up triangle.cpp, square.cpp, and equilateral triangle.cpp. So if we jump all the way into triangle.cpp, and we scroll all the way down to where the read function is defined, we will see these 3 very complicated lines of code. Right? And hopefully you can all pick up on the attempted joke there, right? I said these would be complicated lines, and they couldn't be anything further from the truth. These are some of the simplest lines you have written this semester, yet they are the least straightforward. Right? Everything is about reorganizing and reorienting the way you think. Now, if we were in CS 150, I would have a double side A, double side B, double side C. But if we were in 150, I could give a 150 student I could give a CS 150 student this code and they would be comfortable with it. Right? It wouldn't bother them. All we've done here is said I am passing in an input stream. I am passing in an input stream. I am extracting from that input stream the value for side A, the value for side B, and the value for side C. And this is very similar to what you have to do in assignment 3. You're reading in the value for your cylinder. Now for composite, you'll need a for loop, but for your composite shape, well, and if we look, let's just look at square real quick. You can see for square, I read a single number. And for equilateral triangle, right, I create a temporary variable, read that in, and set it. So same basic process for each of them. Now the only difference in assignment 3 when you start writing it for between implementing your cylinder, you're going to read in 2 values. For composite, you're going to have a for loop. And really, in your composite read function in assignment 3, you're going to end up with in assignment 3, you're going to end up with a line, pretty much this line inside a for loop. And the rest is just making sure you read in the number of shapes and you write the for loop correctly. For example, reading in num polyhedra, writing the appropriate array-based for loop, and throwing this line in that loop. But all we've done is we have extended our shapes interface. We said, now I'm going to provide a stream extraction operator so I can generalize reading in a shape and I don't have to reinvent the wheel each time I want to read in a shape. And because I want to review what we did early in the semester, let's add it to a shape container, shape collection that we've created. Output it for verification purposes, and that's it. But even with all of that, we still end up with the same result. We still end up with, well, an error message, right? Use this message, I didn't supply the input file. Right, input shapes.txt, and there we go. I still get the same shape factory output. I'm still outputting shapes. The only difference is now I'm reading in different values from them from an input file. So different values for my shapes from an input file. I can create non-test shapes with actual values I set through the use of those read functions and dynamic binding and the stream extraction operator. And we can see I print all the shapes a second time, right? With the first one being within the read shapes function so we can verify, and this being the original output within the main function. Now let's take that a step further. Well, there's something here I'd really like to. Now in these examples we've been sticking with the same version of Shape Factory. Mainly a shape factory with an array of shapes terminated with a sentinel value, a shape pair that's empty, and a count-based for loop. Now in example 6, the rest of the code is going to stay more or less the same, right? In example 6, if we scroll down, you see the same code in example 6. Right, this hasn't changed. Right, example 6 is the same as the example 5, but now, you know what? I got bored of the previous version of Shape Factory. Now what I've done is I've removed that last shape pair. We see that now I have 1, 2, 3, 4, 5 elements in my array. And now this is a good emphasis on why understanding interfaces is important. Now this semester, early in the semester now, in the first couple examples, assignment 1 and a couple more, we've discussed the STL container interface, the providing an iterator, providing begin and end functions. And we focus on vectors and lists in that regard and providing them with our own containers. The C++ STL also provides begin and end functions and iterators for arrays allocated on the stack, for arrays allocated on the stack, as I'm doing here. And because of that, because I have an iterator, begin and end functions, I can rewrite these for loops. I have a range-based for loop that references each entry in the known shapes array, takes that reference pair, takes that name and compares it to the name of the shape I want to create. If it matches, it takes that pair, takes the model, and clones it. Now, one thing you might notice is I am using a reference variable instead of a value type variable here. And that's where we go back to the point I made earlier. Earlier, back at the beginning, in the previous part 1, in example 2 of part 1, I noted how I should have implemented the big 3 for the shape pair, but I didn't. I only implemented the destructor. Now, that provides me with a problem. The problem is the compiler does a shallow copy for the copy constructor and a shallow copy for the assignment operator, yet I have written a deep copy destructor, a deep copy version of the destructor. So if I were to do a value type variable here, it would create a shallow copy of that shape pair, then it would delete that copy. But it was a shallow copy, so the pointer in the original shape pair, as it exists in the array, and the pointer in the copy reference the same shape model. And because my destructor deletes it, that block of memory is deleted for both, and that's a problem. So can I work around not implementing the big 3? Yes. Does it make things more complicated? Yes, but I managed to work around it here. And I did some hand waving to shape pairs and implementation details, so I can get around it. But I am still doing the same thing in the loop. I'm simply using a range-based for loop and a reference variable instead of known shapes on. The rest is the same. Is that shape known? Same range-based for loop. If the names match, return true, otherwise return false. But all I've changed, the logic's the same, the condition is the same. All I have changed is the type of for loop I'm using. Then list known, range-based for loop, same output line. Then number known, I've changed to a range-based for loop, and I've incremented my counter. And yes, I could write this another way with size of or something, but this works. And then we get down to the stream extraction operator we discussed from example 5. But that read function, our discussion of the read method, is what you should take away from this. The read method is important, and the copy constructor, destructor, and assignment operator and shape collection should point you in the right direction for assignment 3. Now, the point to an array of pointers, we discussed that in example 2. So what you need to do is convince yourselves of each of these elements, walk through each of these examples, convince yourselves that the mechanics in these examples make sense to you, and then figure out how to adapt them and apply them in assignment